This is Mrs. O'Neill for AP Chemistry, Chapter 11, Section 6, Phase Diagrams. We're going to learn how to read these phase diagrams, which are really just graphs, but they show the equilibria among the gas, liquid, and solid phases. Again, pause, fill in the blanks, and then play to hear my words. So again, a phase diagram is just a graph. It represents various temperatures and pressures at which different phases of a particular substance exist. So every phase diagram you see is really only about one substance and how or at what temperature and at what pressure they would exist as a solid, liquid, or gas. So here's an example. Just quick example. Here we here we'll go red line here. Red curve is your vapor pressure curve, which means your vapor and condensation equilibrium. We have our green line, which are sublimation curve, and that's where sublimation and deposition occur, right? So a solid to a gas or gas to a solid. And then here we have the blue line is the melting or freezing curve. And again, that's where our melting and freezing point is at the same exact temperature. Some other things to look at is that triple point. We're going to need to know what that is, and this critical point. So the liquid gas line usually has an end point to it. So pause the video, read the information, answer the questions, and then play to get the answers. Hopefully you got that, and if you didn't, if you have questions, please ask during class. So the triple point just means that the three phases of that one particular substance exist at that particular temperature and that particular pressure. It has to be exactly that temperature and pressure in order to have all three phases exist at that same time. So the critical temperature is the temperature above which a substance can no longer exist as that liquid. The critical pressure is the minimum pressure needed to keep substances in liquid phase at that critical temperature. And of course, the critical point shows where that temperature and pressure together. So for water, if you have water at 374 degrees Celsius, no longer exists as a liquid. If you have water at 218 atmospheres, anything above that, again, right, this is the minimum pressure that's needed to keep it as a liquid. And of course, that critical point would be where that water liquid vapor line actually ends. So if we look here, again, this is just a generic graph. It shows that it's solid, liquid, gas, and it's always like that, solid, liquid, gas, which should make sense, right? We have that triple point, we have the critical point, and we have where things are at equilibrium. So every curve represents an equilibrium between the two phases. So here again is an example, and we have standard pressure always at 1 atmosphere. That's always something to look at and to keep in mind. Another thing to think about is this water. Water is very unique. Water phase diagram is unusual because the slope of the ice-solid equilibrium line is different from most substances, and it illustrates that ice melts under pressure. Why does it do this? Because of density. The density of liquid water is higher than solid water. You know that most of the time your solid substances will sink to the bottom of its liquid form. However, for water, ice floats. Ice solid form is less dense than its liquid form. So for CO2, that's where the solid is more dense. And most of your phase diagrams, this is how they look like. So we want to also remember that this is 1 atmosphere. And the 1 atmosphere, we know then that the liquid CO2 does not exist at pressures below the 5 atmospheres, right? So if we have 1, there's no way we're going to have liquid CO2. So in your notes, you might want to mark down your solid, liquid, gas area. You want to notice your triple point and your critical point. You also might want to show for water that slope of the solid liquid line is going to be as a negative slope instead of a positive slope. Some of these other words I'm not too worried about. We're not going to go nuts over them. They're not going to be really, really important. So again, here's some other representations. Another thing to note is the normal melting and normal boiling point is going to be at standard pressure. So we want to keep that in mind as well. Standard pressure is going to be where your normal melting or freezing and your normal boiling. See you in class.